Good afternoon, everybody, and welcome to the Pearcey Conversation. I would like to acknowledge both the Gadigal people of the Eora Nation and the Boon Wurrung and Wu Wurrung Wurundjeri peoples of the Kulin Nation, the traditional custodians of the land where the Pearcey Events team meets, works and creates. We pay our respects to the elders, past, present and emerging. We also acknowledge that people are attending, speaking and sharing at this event today from other traditional lands and nations, and extend our respects to their custodians, ancestors, elders, and future leaders. On behalf of the Pearcey Foundation, I want to thank all of you for joining us this afternoon, and a special thanks to our speakers for generously making the time to share with us today their experiences. My acknowledgement also to our distinguished Pearcey friends. For those of you who don't know me, my name's Wayne Fitzsimmons. I am the National Chair of the Pearcey Foundation, and it's my honour to warmly welcome you all. Before we kick off today's conversation for an insight into a very interesting history and future of Wi-Fi, a few reminders. Coming up in October, we have some fantastic events. As part of the Ada Lovelace Day on Tuesday, the 13th of October, 2020, we will be celebrating women's contribution to Australia's digital age, with some fascinating stories and insights to be shared from the likes of Alison Harcourt, Kerry Mengerson, Anne Moffat, Jenny Seabury, and Helen Vorath. It is, of course, our award season, and we acknowledge some amazing individuals already. Grant Petty won the Victorian Award, Grants of Black Magic, and Shane Hill in the ACT won the award there. He's educationalist, mathletics, etc. he's responsible for. As we are all set to celebrate the achievements of some more outstanding entrepreneurs across the country in October, and then of course at the National Awards presentation in mid-November. All exciting stuff for Pearcey interested folks. Now all of these dates are available on our website, and I'd ask that you refer to pearcey.org.au or heritagepearcey.org.au. Now, to kick things off this afternoon, I'm asking our esteemed contributors to introduce themselves. I would love to invite them to each share their own brief history, how they got to where they are today. By way of background, all these gentlemen worked together at Radiata, which was the Australian startup established in 1998 to successfully commercialise the Wi-Fi chip conceived at CSIRO Radiophysics in Sydney earlier that decade. Clearly, all three are eminently qualified to comment on the history of Wi-Fi as well as where it is headed, given all three are still practicing in the field to a lesser or greater extent. And firstly, I'd like to welcome David Skellern, one of the two founding directors of Radiata. Many of us met David post-Radiata whilst he was CEO at NICTA for 6 years, 2004 through 2010. David did an outstanding job in developing that organisation into becoming a powerhouse in ICT research in Australia, and it's now called, I've forgotten. He's continued on from there in several academic roles, Macquarie University, Imperial College London, and so on. However, as he has gone underground for some time, we are delighted he has agreed to surface today and speak on a subject I'm sure is dear to his heart. David, thank you.
Thanks, Wayne. So I won't tell you much about what I'm doing now, other than to say I'm on the boards of quite a few companies. I still visit Imperial when I'm allowed to go to the UK, and I'm working on a variety of things, but really focused in that area on implantable chips. So I want to give you the kind of rapid overview in 5 minutes or thereabouts, as close as I can make it, of the kind of potted history of high-speed Wi-Fi. And I'm going to take you back to the 1980s, late 1980s. It's common in research that unconnected groups working at the frontier of a field independently around the same time converge on a similar set of goals to take the field forward. This was the case in the late 80s when several research projects on high-speed wireless LANs were born. A challenge in getting these projects up was that there was negligible customer demand or even interest for such networks. And so the business case was pretty unconvincing. In retrospect, this seems odd because to some of us, it seemed a bold but natural direction because of the state of developments in computers and communications. Across the 1980s, across the 1980s decade, computers had evolved from mains-powered mini-computers to desktop and luggable PCs through to battery-powered laptops and handheld PCs right at the end of that period from about 1986. And in the telecoms arena, 1989 saw the release of the first true mobile phone, the analog Motorola Microtac 9800X, about the size of a brick or not much smaller. But at the same time, the development of the first GSM digital mobile phone standard had commenced. Computer networks in the late 1980s had become widespread in office environments, having started in about, well, a bit before 1983, but Ethernet was 1983. Now, these were mostly wired networks operating at or below 10 megabits a second transmission rates. By 1989, 100 megabit per second optical fiber networks were becoming available, the FDDI system. Against this background, the researchers who started wireless LAN projects anticipated a future in which people would make use of multiple portable connected devices, computing devices, without being restricted to a desk area by wired network cables. The networking would be unplugged. Now, there were a few wireless networking products at that time, but they were operating at very low speeds, from 30 kilobits per second, and I seem to recall one that was up to 150 or 200 kilobits per second. The more ambitious wireless LAN research projects, and there were several, as I said, set their target data rates at or above 100 megabits a second, some 3 orders of magnitude faster than the available wireless networks at the time. And the next decade of wireless LAN research and development would usher in the era of mobile computing. Now, while early WLAN research projects considerably advanced knowledge in the field, I'm going to talk about the one I was involved in, and that one proved to be especially significant in the development of scalable high-speed Wi-Fi. So that was the project carried out by a joint team from CSIRO, which is where Phil was at the time, and Neil ended up partially there, and Macquarie University, which is where I was and Neil was also at. The main outcomes of this project were threefold. People would say there were many more, but these are the main ones. The first was a landmark WLAN system patent submitted in November 1992 by CSIRO and awarded in 1996. CSIRO received over 500 million Australian dollars in license royalties over the life of this patent. The patent described a system that transmitted and received on a half duplex channel using multiple sub-channels and included, among other elements, an FFT with cyclic extension, forward error correction, interleaving, data packetization, and an antenna switch. The patent basically said, if you want to do high-speed wireless LANs, this is the way you'll have to do it. And indeed, that's turned out to be the case. The second outcome was a complete working 27 megabit per second wireless LAN system that we first demonstrated in 1996. And that operated at 40 gigahertz. And then in 1997, we got it working with 5 gigahertz radios because the National Information Infrastructure Band had been opened up in the US, and we thought that would go worldwide. And the third major outcome was the 1997 spin-out of Radiata, which designed and demonstrated a 2-chip CMOS implementation of the 54 megabit per second IEEE 802.11a 5 gigahertz standard physical layer. In September 2000, we demonstrated that. And soon after that demonstration, Cisco acquired the company for 565 million Australian dollars. except we didn't get dollars, unfortunately. We got shares in Cisco that then proceeded to tank over the next few years. 3 members of the Australian team, including me, were recognised by the IEEE in 2017 for pioneering contributions to high-speed wireless LAN technology. And that recognition was through the award of the Consumer Electronics Technical Field Award. And what was great about that was that, not that a few of us got it, because the whole team contributed to it, but that it recognised that Australia had made that leadership role, taken that leadership role, and were the pioneers in it. Because there are a lot of other parts of the world that believed that they were pioneers and were claiming the same thing. Now, our wireless LAN project could very well not have happened when it did. In October 1990, John O'Sullivan at the CSIRO, he was the head of the group there at the time, and I and my team at Macquarie University had submitted a proposal to the first round of the new Cooperative Research Centres program, newly introduced that year. And we wanted to get funded for a Centre for Local Environment Communications Technology. Unfortunately, it was culled in the first review round, and it could have just died at that, or we might have only got very small amounts of money. But in September of 1991, the CSIRO decided to start, in fact, it might have been July, but whenever in 1991, decided to fund the whole project, and very generously. And that's what made it happen. Now, quite a lot's been said over the years about the radio astronomy connections with our wireless LAN work. And while that was true in the research phase, the commercial implementation needed to draw in knowledge and experience from far wider backgrounds. And so we have people like Neil, for example, in there, among many other brilliant people. A key factor, though, in the CSIRO Macquarie's team's early appreciation of the superiority of their multi-channel system design was the fact that a number of team members in both organisations had previously worked together over many years. And they'd also worked separately on designing and building radio telescopes. That background taught us a lot about how to design and build complex systems, including the development of novel, efficient, high-speed chip implementations of FFTs and error correction codecs, which was central to the wireless LAN system. And the fact that we realised that the multi-channel system was important was really demonstrated because it was rejected by multiple standards bodies throughout the 1990s. As a mechanism of developing high-speed LANs. So it wasn't until late 1990s that the merits of the approach were accepted with the 1999 ratification of the 802.11a standard. And I'm just going to end by saying subsequently, all 802.11 physical layer standards, and indeed the 4G and 5G cellular systems, all use this multi-channel or OFDM signalling, albeit now with added powerful diversity extensions. Okay, so that's my 5 minutes, I think. So I'm going to leave it at that, and you can ask me any questions you like later.
Oh, thanks, David. Now over to you, Neil, the other founding director of Radiata, in fact. Neil was also a co-founder of Morse Micro in 2017, where he is VP Engineering. Now, Morse Micro is focused on long-distance, low-power Wi-Fi chips for the Internet of Things and allied applications. So he's well-versed, he's well-qualified for that role. Neil has a special place in the Pearcey family, as he was awarded the Pearcey Hall of Fame in 2008. And as a former semiconductor guy myself, I recall Neil's name as the guy who wrote the textbook on CMOS. So Neil, in my consideration, is right up there as a pioneer in the semi business, and he's still at it. Neil, over to you.
Thanks, Wayne. Yeah, Dave, that's an excellent summary. And thank goodness you got the memory to remember all of that stuff. Mine's going to be a little bit more personal, a description of my personal journey. So it starts actually with meeting Dave. You know, we got to know each other in a beer garden in Munich, along with Richard Keeney. We were at some conference and we kind of got together. And I was in the US with a chip company doing contract designs for various companies. And we at my company were looking around for things to kind of get our teeth into, but we had no domain expertise. That is, we knew how to design chips, but we weren't communications people. And Dave had this carrot that he dangled in front of me, which was, look, CSIRO's working on some really interesting stuff, and it looks like this. And he sketched it up on a whiteboard when he kind of got back to visiting us in Boston. And he snagged me. I looked at this and I thought, this looks really interesting. I didn't understand it fully, but it looked sufficiently, he could describe it in about, 3 pen strokes on a whiteboard. So what that ended up happening was after 20 years in the US, I upped and left and came back to Macquarie with a contract for 5 years to do research in this area. We were kind of lolling along there, and at one stage, I think it was my wife at the time says, "Are you going to start this company or not? If you don't, I'm going back to the US." So I went into Dave and actually Terry Pearcey and said, "Look, we better start this company or I'm going to have to go back to the US." So that's how we started Radiata. And Radiata had a couple of key components, as David said. It had the background of the theory of OFDM modulation and coding and all of that. And the other key part that made it, in the end, a commodity item, was the fact that I'd had, I guess, almost a lifetime experience in CMOS, starting off at Bell Labs, writing a text on the subject and being across what CMOS could do and couldn't do. And the key factor in CMOS technology is that in addition to digital, you can also do analog circuits and you can do radio frequency circuits. So what that means is it's a true system on a chip technology. So that means you can get everything onto one chip. Now, it's got crappy analog performance and crappy RF performance. At least it did at the time when we started Radiata. And so you have to kind of do a lot of innovation to make that work, a lot of engineering that basically hadn't been done before. You've got to make a production-worthy chip that will work, for all across all the variations that you can have when you manufacture a CMOS chip. And those variations are something like 3 to 1. So one chip might work 3 times faster than the other, and you have to take that into account. So in essence, the engineering of those chips is the thing that Radiata contributed and made it valuable. So it went from patent, which is ideas and theories, into an actual product you can manufacture. I'm sure we'll hear from Phil in the future in his talk about how that's kind of progressed. So at the back of Dave's desk there is the first RF chip that we did, which is a 5 gigahertz transceiver for OFDM. And that was very innovative in the sense that it had all the blocks that you needed to do a full radio receiver and transmitter. And previously, those things had been done as individual chips on boards, and each board had to be kind of tuned up by a lab tech to make it work. So the cost of those radios, those Wi-Fi, well, they weren't called Wi-Fi, but WLAN radios at the time was extremely high because each one was almost hand built. Once you stick it on a chip and you can make it work over the process variation that you have to deal with, and you make it manufacturable, you basically brought that down, that cost asymptotically to zero. And that's why in the last 20 years, the chip costs have gone drastically from, you know, dollars or $10, I think we were talking about, down to sub-dollar. And that's what's led the revolution there. So Radiata did this, the 5 gigahertz chip. It did it in 180 nanometer technology, 0.18 microns. And after a time at Radiata and Cisco, I kind of got sick of it. I left. I had an intermediate career in the aviation industry and created a company that does all the electronic flight books for pilots in Australia and a lot of other countries. And then, meanwhile, back at the ranch, Phil and Andrew Adams and the various key guys at Radiata had started another company called G2 Microsystems, which transmogrified into Broadcom here in Sydney. And they were still designing very advanced Wi-Fi chips. And if Phil doesn't say it, I'll say it now, that those chips basically are in your iPhones and your Samsungs right now. So the chips you use in your everyday use have actually been largely designed here in Sydney by Phil's team. Now, a couple of guys came out from Europe, from Belgium and Scotland to work there. And at the appropriate time, they decided that it was time for another Wi-Fi company. And that was Andy Terry and Michael Denil, who were working at Broadcom. And around about that time, I was coming to the end of my aviation career, mini career. And they asked me whether I'd join them to do yet another Wi-Fi chip, but this time rather than high speed and medium distance, this was for lower speed and long distance. So, so I joined them with Morse Micro, and that's in essence what Morse Micro is doing now. It's doing chips that are very low power, very low cost, very like 10x the range of regular Wi-Fi, but at 10x lower data rate. And you see a chip behind me here. So Dave, I think the chip behind you had something like 1 million transistors in it all up, with a lot of memory transistors. The chip behind me has, I think, something about 25 million transistors. So 20 years has packed more transistors. This one's got 4 32-bit microprocessors on it. The one that Dave's got had one 16-bit processor called the Rad16. So, that's a brief personal history there of, you know, my involvement in Wi-Fi. So back to you, Wayne.
Well, thanks very much, Neil. I find that absolutely fascinating. But yes, that's great. Now to Phil, who's also worked at Radiata as its first employee.
Second.
Of course, Phil has gone on to greater and better things at Broadcom after his starting up G2. And Broadcom's acknowledged as the largest semiconductor company in the world. And he's still focused on Wi-Fi, as he's responsible for, amongst other things, all the Wi-Fi chip design inside Broadcom here in Sydney. And we now know the history of why that's the case. But I mean, as Neil said, your iPhone and your Samsung phone, you know, they've got Broadcom chips in there, and the Wi-Fi chips are designed here in Sydney, which is fantastic. Phil's eminently qualified to speak about the future of Wi-Fi and its future relevance. By the way, he's no doubt going to let us know some trade secrets on how Broadcom will remain world leader in this field. Over to you, Phil.
Thanks, Wayne. So I'll give a very brief personal flow which follows a lot of what Dave and Neil have just described. So I was lucky enough in the late 80s to be studying electrical engineering at Sydney Uni, and I had this fantastic electronics lecturer, Dave Skellern, who we had for 1 year, and he was exciting enough, and then he just disappeared. So I didn't know where he'd gone. And subsequent to finishing at Sydney, I started working at OTC, the Overseas Telecommunications Commission as it was back then. They had a group called the Satellites and ICs R&D group, and my boss at the time was Terry Percival, who had previously worked with Dave. Anyway, shortly after I started there, I think within a year, Terry had left OTC to work at CSIRO in this new group called Plans under John O'Sullivan. And a good friend of mine, Andrew Adams, was also working at OTC, and we both talked to Terry and decided we would jump ship and move to CSIRO because it sounded like pretty exciting stuff. Not that OTC wasn't, like that was actually a great spot too. And we started at CSIRO in about 93, I think, and that was working with this PLANS, a program for local area networks that Dave mentioned earlier under John O'Sullivan and Terry. And so I think I spent a couple of years there working on building these rather large boxes for ADCs and DACs so that we could actually sample the wireless environment at 60 gigahertz to see what it looked like, because quite clearly to develop some new wireless local area network system, we needed to understand just what the channel looked like as you moved around a typical office. So that was took up a surprising amount of time actually doing that. And along the way, I moved into doing a rework of an existing serial FFT chip, which had been developed for audio work by Colin Jacker and a whole heap of other guys, into parallel 50 megahertz 16-point FFT, which was sort of our first foray into how we could do a multi-channel, OFDM style system. Anyway, after some years, about I think it was 98, when I've been working with Dave and Neil for a little while by then, and they had started Radiata, I was seconded from CSIRO to work with them, working on this with Richard Keeney, who's another old sort of, it's very incestuous, the whole story. And I recall talking to my wife at the time saying, I think this is going to really go off. I think I want to leave CSIRO and work for them directly. And I think I had to almost beg Dave and Neil to let me work with them because we had an agreement with CSIRO in terms of seconding, and I'm not sure that was, yeah. Anyway, so fortunately I did get to work with them. And so, worked with Dave and Neil and Andrew and Richard and all these guys for some years at Radiata, and then, the excitement of getting acquired by Cisco. And then some years later, we all had fallen out of love with Cisco, not with each other. And so I went to, actually, so I was not a founder of G2. That was Andrew and Jeff Smith and a few others. So I was talked into that by Andrew, who in turn I had talked into coming to work at Radiata way back when, because he'd been off in Leeds doing a PhD in power combining for radios. So we all worked at G2, working again on Wi-Fi chips, 802.11, but looking for location tracking and sensing. So we did an insane amount of work on that, but unfortunately the market just wasn't there at that stage. And in about 2010, we ended up being acquired by Broadcom. And so from then until now, I've been working at Broadcom as part of a team. Like we say we design the chips in Sydney, but we also have groups spread over 4 other major locations in the US and Israel and India. So we actually work quite closely with all these other teams. And the real thing that working at Broadcom has been about is, well, 2 things. One, the insane quantities of chips that we actually produce, like, and we're talking hundreds of millions, means that process control is an immense issue. You have to, as Neil mentioned earlier, with CMOS, the actual process variation from chip to chip is quite large. And so there's an immense amount of work ensuring that the designs are robust under both the process changes and also temperature, voltage changes, and aging. And our customers are also insanely picky about performance. They really don't like to see variation. So there's a lot of the work we do is really ensuring that no matter what happens with the chip's external environment or indeed changes on chip, that the performance stays the same. And also guaranteeing that we can produce these chips at these massive rates with a very low overhead in testing, because each of these chips has to be tested, because if you've got a faulty chip and it eventually makes its way into, say, a phone, which is perhaps worth $200 of goods, if you then have to throw away the whole $200, again, the customer is very unhappy. And that's basically brings us up to the current date.
Thank you. Thanks. That's wonderful. Fills in a lot of missing pieces for me personally. Now, no doubt there's some questions coming, and I'll come to those. But I'd like to kick off by asking the contributors of their personal perspective and vision for the future. What are your thoughts on where things are headed and how history might inform the future? So, David, I'll go to you first. What are some of the new directions and roles and applications Wi-Fi might perform near term and longer term?
Yeah, okay. So, you know, this is a tough question, of course, right? Well, there's some famous quotes about this I won't make about predicting the future. But in thinking about today's talk and the fact that I knew you were going to ask me this, I went back and read the very first proposal we had, which was in that CRC bid. And I still believe that that's not a bad way that things will go in the future. So it's been terrific seeing the huge build in bandwidth that's been needed as a result of the COVID-19 situation, the lockdowns, the large, vast increase in network traffic, and the fact that people are expecting to have fabulous performance inside their homes. I, for one, have found the Wi-Fi network to be completely unreliable. So it's a bit worrying that I can't even make mine work very well. But most of the problem has got to do with the size of my house and the fact that it's all concrete, or a lot of it, and that the outside's clad in copper. So I have a pretty lousy external signal. And I don't have a great, I'm afraid the network, the particular devices I have, manufacturer will remain nameless, just don't cut it in being able to meet the requirements inside the house. And in fact, the best performance I've ever had in this house were the very first Wi-Fi access points we got from Cisco that used our own chips, because I reckon they perform better in terms of capacity and signal to noise ratio overall in a particular area than any other chips I've ever seen or any other systems I've ever seen. So I think reliability is very important, but I digressed because I started talking about the COVID situation. So let me read you the first two sentences of the wideband wireless networking system that we proposed in the CRC proposal and ended up being the one that CSIRO and Macquarie got together to build. We said that we envisage a picocellular wireless network that couples into standard data networks of different varieties and allows the user to freely access the full power of the network without wire or fiber connections. This network would operate within the confines of a chosen environment. So I think if we set up that architecture, first thing we need in networking is to get the bloody fiber into the home, for example, and in all offices. then you've got a high speed, or you at least potentially very high speed into your environment. And I think we're going to need to have much smaller networks than we have now. Even back then in 1990, I figured that we were targeting then the 60 gigahertz region because it had a lot of bandwidth, and we were able to build large systems, build systems that would be able to have very high speeds. And I still think that the way this could go in the future, if people wanted to do it, since these chips cost bugger all, is you just put them in, everywhere you've got a power point. Just have them pumping out there in each room in your house, and or in an office. They can be everywhere and manage the different frequency diversity. I mean, there's a lot of issues to overcome, and there's a lot of roaming issues that still aren't really solved unless you buy complex, expensive systems. And all of that can be done, and the architecture would give us a really great access inside the home. And then I think the sorts of technologies that we've got with that people like Morse are doing, and perhaps intermediate technologies for intermediate ranges, you could imagine just having a layered network of different cells, large cells, smaller cells, and smaller cells inside your home, and so on, that would allow you to actually use Wi-Fi in lots of places. Doesn't have to be everywhere, because 5G stuff will eventually work, and it'll be available, it'll have high capacity, but we're still quite a few years off that happening, I think.
So that leads to a question I've got for you, Neil, is how do you see 5G and 6G and the like working with Wi-Fi down the road? Will they duplicate each other, or will they be complementary, as Dave just outlined?
Right. I think they're largely complementary. They're basically the same technology, and the way I think about it is that one you pay for and one you don't. So Wi-Fi is the free network, and it'll get used where people don't want to pay for things. The second, kind of thing that goes along with that is that when you deploy 5 and 6G, you have to kind of do a proper, building of a base station, et cetera, With Wi-Fi, basically, you've got billions of installers, because all the installer has to do, or the installer is you or me, and all we have to do is go to the shop, buy a Wi-Fi access point and plug it in. So I think just like now, they'll be used where they need to be used. I mean, if you want to guarantee access and your data is worth a lot to you, then you'll use a telco network. If it, you can stand the vagaries of, free spectrum, like interference and stuff like this, then you'll use the free stuff. And there's kind of, I think I'd mentioned previously when we met last week, that they've deployed phone networks in places like Myanmar, where they've deployed Wi-Fi phone networks where the cost is an order of magnitude below the cost of the telco networks. You always need the telco network there as a backbone, but when you get out to the edge, you can do other things. And technologies like Morse's technology, which extends the range at lower data rate, will play into that. Just as Dave said, I believe Dave's hit the nail on the head. Basically, you look at kind of seamless coverage from basically centimeters out to kilometers, things like that. I also think that perhaps in the future you may be able to build the Wi-Fi into the wall. So just like you can build electrical distribution into walls as you build buildings, we can build Wi-Fi into the wall, so you operate at the lowest power possible, so you don't have any health concerns, but it's seamless and it's available everywhere. It's like a mist. So that's basically what I think.
Well, thanks. I think I'd agree with you that. No, I've got one question here from Glenn Downey, and Mike Nichols has been involving himself there as well. But for Phil, you must face this, you know, as a reality in your job. Where do you find the people who've got the skill sets and the training to do all these designs and think about the future requirements?
To a large extent, we've relied very much on people coming to Australia for, you know, all sorts of fairly obvious reasons that they actually would like to come to Australia. So we have benefited from the education systems of other countries to a certain extent. I think at the start, you know, most of the senior people were local. We're talking, because we're a Sydney-centric company, or this group is, you know, University of Sydney, UNSW, UTS, Macquarie. But, you know, increasingly over the last 10 years, most of our new staff, you know, I'd say 60% have come from overseas. And so that's, depending on how you see it, either a blessing or a curse. In terms of why we don't have people locally, I'm not, you know, really sure, and I'm not that qualified to talk on it, but certainly there's a difference in the environment to when, for instance, I was starting, where there are a large number of groups like OTC, Telstra in Australia, who were employing a lot of young grads to do, you know, fairly innovative research that was somewhat undirected. I think also, you know, places like Bell Labs, where Neil was, would hire a lot of young grads and early career researchers, and most of those places do seem to be drying up. Now, does that mean we should be encouraging government to fund large organisations that are monolithic and can carry the cost of actually hiring lots of young grads to train them up? I'm not sure, but certainly it seems to be a factor.
Right. So I want to ask the same question a bit differently to both Neil and David. So Neil, you have the requirements to find these people, but also you've got a foot in the academic world as well. How do you balance that out? Do we rely on immigrants, or can we introduce tech training courses or academic courses?
Well, first of all, I have to probably publicly apologise. One of the ways we got some employees is that we let Phil do the hard work.
You stole them.
The second way, well, yeah, we promised not to do it anymore. Well, we're much larger now, so we do the same as Phil. We have to import, and then personally myself, I've had various programs that I've supported at universities to try and train. I mean, there's a limit to how many people I can train, but if there's someone interested, I've, especially, you know, some years ago, I've kind of trained them up, and they've gone, you know, in fact, one at UNSW went straight to G2. Two of the others one of the others went to Broadcom in the US and then came back here, and now he's in Mavandi in Sydney, and he's doing millimetre wave CMOS radio or CMOS radios. So it's if you do it yourself, it's almost like a craft profession. You've got to kind of, you know, glom onto some graduates who have some interest and then kind of bring them along. But, you know, it takes a lot of effort, right? And there are centres, there's still centres of excellence in chip design, especially University of Adelaide, who haven't given up on it, like most of the other universities have. But it's a struggle. And I think, you know, the main thing is if you go to a class of year 12 and they say, well, what are the prospects in chip design? You've got to be saying, well, you know, there's a couple companies, but on the whole, if you want to be an accountant, you're probably better off there. But
Yeah.
which, you know, it's a very, very small community here. So it's all, like as Phil said, it's, you know, almost incestuous, right? I mean, you almost can't move without knowing virtually everyone who's in the industry here. But, you know,
Australia to keep this skill set up? Or
yeah, all we do is that we do a case by case, right? I mean, it would be good to have a lot of
to other
support,
countries.
but, you know, you've just got to do it piece by piece.
There are some other groups that are working. So Macquarie's still got an RF chip design team there. Simon Marn's leading that, and they've got very good funding from Analog Devices.
Right. Yeah, I forgot. You're right.
And there's a team that designs chips, RF chips among them, for down in Melbourne, that works for AMD, whoever they are now. Are they still AMD?
Yeah, right.
So that's a group that, and that core of people came out of University of Melbourne and were developed in NICTA under Stan Skafidis's lead. And Stan still is doing microelectronics work, although he is focused a lot more now on nano devices and nanoelectronic systems, but coupled with CMOS designs where necessary, where needed to do a lot of the input-output. So,
Right.
So those things are happening, but they are small because there's really only, you know, Stan and one other person or something, and then Simon and I think Tony Parker's still working with people out there on their modelling and so on, assessment of devices and circuits. So it's a tough thing to do. The emphasis in Australia has just moved away from hardware. That's the problem, I think, and I think that's a real problem. So I call it straight what it is. It's a problem, and there seems to be a view that you know, so just concentrate on software and on data analytics, big data, and so on. And that's the future, and that's where people are going to make their fortune in the future. So there's been a succession of leaders of large research groups who have cancelled all the work in hardware. So CSIRO has done that. Even DSTO was doing some work there. I'm not aware of them doing any anymore, but that might be wrong, but because I'm a bit disconnected from them. But I think that's disappointing. But it's after fighting if you like, I feel like after fighting the good fight, I'm just going to acknowledge, Glenn, that you've been after me for a while, Glenn Downey, to respond to some questions you want to put about getting a microelectronics industry going in Australia. And I just think it's too bloody hard. You know, I devoted a lot of my life to trying to make that happen. And
just one more mint.
That's right.
One more mint.
That's right.
Never say die. Never say die.
I know. But ultimately,
as long as we're breathing, right? If we're not here, then no one knows, right? I mean, so the only one, you know, you got to fight the fight.
Well,
but I know what you're saying. I know what you're saying, but
well, I
would think like that sometimes.
Yeah,
I'll have another go. Yeah,
good on you, mate. I think that's terrific. I'm having a go in Europe. It's a lot more fun there, I've got to tell you. So
well, that's of no bloody use, mate. Come on.
No, it could be.
So
I'm doing exotic stuff again. So we're putting memristors on top of chips we get from up to sort of process level unpassivated. And then we do post-processing in exotic technologies on the top to actually drive memristors. And we're looking at the use of memristor circuits to dramatically reduce the size of chips for certain functions.
So just on a positive note, you know, your former chairman at Radiata, Chris Baer, he and I are on the board of Coda Wireless in Adelaide, and we did the original chip design, which was an 802.11 N or
Yeah.
H, was it, whatever, the mobile. But we've moved up the food chain, but we're still making hardware, albeit sourced outside Australia, but shipping it all around the world. And so it's this. We need hardware designers there. We have a lot.
Yeah. I'm also working in Australia with a company that does Wi-Fi developments for system developments using other people's chips, but Wi-Fi for agricultural work.
And then there's Morse. Look at Morse. Morse is your model little company, right? It's like hardcore Wi-Fi here, right? There's no one that does it like it. We've got security, low cost, tiny chips, highly manufacturable, long range. And you know, the interesting thing is that you can cycle around 20 years and do the same thing twice and people don't notice, right? So I find that amazing, right? It blows me away.
So
Here I am again.
Is there anything that government can do from a policy point of view to protect and develop this industry, or is it just laissez-faire?
Mate, there's shitloads they could do, but you know, how many times do you have to beat your head against that wall? Honestly, we have pathetic governments.
Right.
We're just wasting our time with government. I mean, I actually seriously have decided we waste our time with government. We're better off just getting out and doing it ourselves.
Well, not actually saying that. I will say this, is that I was supported by CSIRO when I came back, but I must admit that my personal philosophy is exactly what Dave said. I thought the only way to you can't lecture people on how to do things. You've actually got to show them how to do things. Yeah. And so I don't rely on government, although they've been very supportive at various stages. I can't, you know, IR&D grants, you know, research grants, various stuff like that, but you can't rely on it. You must, you know, have a path of your own, and most of the significant stuff has been done while the government's been there in the nascent. I mean, the government was very supportive of Radiata. If they hadn't given us a commercial ready grant in the first year, we would have been knackered, right? So we have to give full credit for that, right?
Yeah.
But in general, in terms of vague programs, you know, like let's, you know.
Well, they don't have any program like that anymore.
No, and look, I've been talking to Glenn too. And I mean, I think there are really good case examples of what you could do now to help the industry now and help people kind of who are not in the basic thing is if you have a fantastic technology there, CMOS in its system on chip capability, but no one knows how to do it. And what you want is you want the people with the domain expertise, like the people doing high rate face recognition, you want them to be able to use chip technology, but without becoming a chip company. So there's a way of doing that I think Glenn is working on, right? So we'll see whether that works, right? If we can kind of pitch that, I think that there's you know, you can't do things traditionally. Like for instance, Morse doesn't have a back-end team. We actually don't place and route our chips. It's done in Belgium, right? Right. So that's a big departure. So we saved a couple $1 million a year by not doing that. It's a risk because you've got someone else doing a critical step for you. But in the early stage, it worked really well. Now we'll bolster that up as we grow the company, but that kind of thing, we need to kind of look at some of the things. I'm not saying Morse is kind of perfect or whatever, but Michael and Andy have done some very innovative things in terms of the business, which we can apply generally to Australia if we want to kind of do it. There's a lot of technology here that can be broadened out and used without turning into a chip design. We don't want to be a chip design, or one doesn't want to be a chip design company, because you want to be building products, because the value add is at the product level, not at the chip level. So the higher up the food chain you go, the better. But if you have silicon, you know, sensor-based silicon that's linked to CMOS, to RF, to digital, a lot of processing power with normal programming and stuff. It's very powerful stuff. It's the technology that everything's going to be based on. And if we kind of ignore it, we're going to miss the boat again.
So
Right?
look, in the interest of
Can
time,
I just
sorry.
say one thing? Sorry, Wayne. I just wanted to, I need to just pull the foot out of my mouth a bit. I said CSIRO doesn't do hardware. That's wrong. So I actually chair the Australia Telescope Steering Committee. And I can tell you that the hardware they're doing is amazing, but it's not chip hardware, right? It is unbelievably fabulous hardware. And the level of expertise and the system design expertise and their ability to exploit these really advanced RF-based FPGAs that, you know, people make, Xilinx and so on, and what they can do with them and build is just extraordinary. But they don't do chips. So there is some hardware there, quite a lot of hardware, and it's state-of-the-art hardware in building radio receivers, especially for radio astronomy.
The other thing that we need is
But they
stuff
live in the
that's
smell of
commodity.
oily rag.
You need commodity stuff that you can sell to lots of people. That's what builds the economy of the country, right?
Yeah.
In addition to the background knowledge to know what to do next, right? Yeah. So that's the role that CSIRO performs, right?
Yeah,
so
that's actually, you remember when we did Radiata, everyone said, oh, you want to do a niche chip. Everyone's telling us, if you want to be semiconductor, go niche, go niche, go niche, right? Yeah. And that was exactly what you shouldn't do.
So in Radiata, you demonstrated collaboration between CSIRO, academia, and industry.
Yeah.
Can we replicate that, or is CSIRO, you know, they've got their own fund from you guys, and they're out competing in effect with the industry, or is that not the case? How do you?
No, I don't think so. I mean, I think again, CSIRO has been very supportive in indirectly to even Morse, right? So no,
yeah, I think it's possible.
I think things are working there well.
Yeah, you need to get the few unique characters who really want to do it, right?
That's true.
In CSIRO, as I said, you know, the area I was talking about where they've cut out their hardware is in Data 61, which is where NICTA went.
Yeah.
So NICTA and the CSIRO ICT Centre joined to form Data 61.
Well, listen, we'll have to draw it to a close, but
I'll just say one fundamental thing right at the end, right? Yeah. Like if you just do software, everyone else in the world can do exactly the same as you. If you've got some hardware at the base that's unique to you, that's the winning thing.
Right. Okay. Well, look, I think I'm totally in awe of what you guys have been able to say and tracing your history through. And I'm optimistic. The question is, can we get entrepreneurs? Can we create an environment which the government can do, where people feel they can have a go and they can raise the money? And I think the environment is pretty good, but it can always get better. So thank you very much for a very well thought out and your presentations, and I've learned a lot and I appreciate it. Before I close, I just wanted to give a heads up on a few things. We've got this women's event on the 13th of Ada Lovelace Day, and if you don't know who Ada Lovelace is, please look it up on the web. She's a very important woman. We encourage you to head to our website and keep up to date with all of our upcoming events and initiatives, and anything that you may have missed. All of these events are on YouTube, and this one will be up in a few days. And I encourage you to keep this. Sorry for the clock. The Heritage Project is, namely the book, is in full swing. We're expecting Volume 1 to be released at the end of this year, which is very exciting. Unfortunately, it'll cut off before these three gentlemen can be included, but the next revision of this edition of this book will come forward and include these three gentlemen. This is an extremely important and equally massive undertaking, which of course takes time and dollars. And if you're interested in contributing as a sponsor of the project, I encourage you to reach out personally or the team at Slattery's. So thank you all again, and I hope you have a lovely evening.